In part 1, we tracked how Einstein got to his two postulates. Now we're in the part where those postulates force a choice. Either your everyday logic about speed is wrong, or the single measured fact about light is wrong. And every experiment ever run votes for the same side. The moment you accept that light moves at the same speed for every observer, no matter what, you get backed into a corner where time and space have to bend to protect that fact. This video is the step-by-step version of that forced conclusion, drawn straight from the arithmetic, starting with the most basic intuition you have about how speed works. That intuition about speed is actually a named thing. It's called the Galilean transformation, and it works perfectly for everything you've ever thrown, driven, or watched move. Speeds add up, speeds subtract, and the math is just addition. Simple. Einstein's two postulates sound almost too simple when you first read them. The first one says the laws of physics work the same way in every frame moving at a constant speed, so no experiment you run inside a smoothly moving ship can tell you whether you're moving or sitting still. The second one says light travels at the same speed in a vacuum for every observer, no matter how fast the source is moving or how fast you're moving toward it. That second one is where your Galilean instinct kicks in and immediately gets it wrong. If you're flying toward a beam of light at half the speed of light, every part of your brain expects that beam to close the gap faster. It just seems obvious. But every experiment ever run says no. The beam still arrives at exactly c, the same speed it hits someone who isn't moving at all. And it doesn't matter how fast you're chasing it or running from it. The number doesn't budge. That's what the Lorentz transformation is built on. Light doesn't add or subtract your speed to its own. It just stays c. So if the speed can't change, something else has to. Speed is distance divided by time. And if the answer to that equation is locked in place, then the markers on our watches and rulers are the things left to move around. The universe protects the speed of light by bending those instead, which makes time dilation feel less like a mystery and more like a trade-off you're forced into. This isn't a loose idea or a philosophical interpretation. It's straight arithmetic. Einstein didn't come up with it to be surprising. He just followed both postulates to the only place they lead together. And the simplest way to actually see that trade-off happen is to build the most basic clock you can imagine. So take two mirrors facing each other with a single beam of light bouncing between them. Every round trip is one tick, and because light always moves at the same speed, every tick takes exactly the same amount of time. It's a perfectly honest clock. Now put that clock on a spaceship, moving sideways at 80% of the speed of light. From inside the ship, nothing feels different. The beam still shoots straight up, hits the top mirror, comes straight back down. One tick, same as always. But watch that same clock from the ground while the ship flies past you, and the beam doesn't go straight up anymore. Because the whole clock is sliding sideways as the beam travels, the beam has to cut a diagonal path, going up and forward, then back down and forward again, tracing out a long triangle instead of a short straight line. That diagonal path is measurably longer, and you can prove it with basic geometry. Draw the triangle, apply the Pythagorean theorem, and it's clear. The beam covers more distance per tick when the clock moves than when it sits still. The light travels a longer road while the speed stays locked at c, so the only thing left to adjust is how long each tick takes. The clock runs slower. That's time dilation, and it's not a perception trick or a measurement error. The moving clock genuinely ticks fewer times per second because the light inside it has a longer road to travel. The Lorentz factor is the number that tells you exactly how much slower. It's calculated from your speed relative to the observer. And as that speed climbs toward the speed of light, the factor grows fit, meaning the time gap between frames gets wider and wider. From inside the ship, though, your clock feels completely normal. You don't feel anything slow down. It's the person on the ground watching your clock run slow. And from your frame, their clock is the one running slow. Because from where you're sitting, they're the ones moving. Both of you are applying the same rules correctly, and both of you are right about your own frame. Those two truths just don't match. That disagreement about whose clock runs slow points to something even stranger sitting underneath it. Picture two lightning bolts hitting both ends of a moving train at the exact same moment. At least, that's how it looks from the platform. Someone standing on the platform watches both strikes land simultaneously and calls it done. From where they're standing, those two events happened at the same time. Now ask the person sitting in the middle of the train. Light from the front strike reaches them first because they're moving toward the front of the train and away from the back, and light from both strikes travels at the same speed in all directions. So the front strike's light wins. The passenger doesn't just receive the signals at different times, though. They have a different plane of simultaneity, a different slice through the coordinate graph of events, and working from that slice. Using the same rules the platform observer used, they prove the front strike actually happened first. Not that it felt like it happened first, that it did happen first, because the laws of physics, including light's consistency, demand it. So you've got two people applying the same logic correctly and arriving at opposite conclusions about the order of events, and neither one is wrong. Both are right within their own frame. So now isn't a single flat moment stretched across the whole universe. It depends on your angle of travel through space-time. What at the same time means depends entirely on how fast you're moving when you ask the question. Simultaneity isn't a built-in property of events sitting out there in the universe, so two observers moving relative to each other will physically disagree about which thing happened first. Minkowski's space-time diagrams make this concrete. Instead of treating time as some invisible backdrop, you draw it as a real axis on a graph, right alongside the spatial dimensions. Every event becomes a point, and what one observer calls the same moment is a flat horizontal slice through that graph. A moving observer's version of the same moment is a tilted slice through the same graph, cutting across it at a different angle. And all of this, the slow clocks, the disagreements about order, the tilted slices, it isn't just something that lives in thought experiments. Atomic clocks flown around the world on regular flights, and then compared to identical clocks that stayed on the ground, came back showing less time had passed. Not by much, because planes move nowhere near the speed of light, but the gap matched what the Lorentz factor predicted almost exactly. GPS satellites deal with this every single day. A satellite moving at orbital speed loses about 7 microseconds per day because its velocity slows its clock down, but it gains about 45 microseconds per day because it sits higher up where gravity is weaker. So the net result is that GPS clocks run roughly 38 microseconds fast per day relative to clocks on the ground. Both of those effects get corrected for constantly, because if they weren't, your GPS position would drift by about 10 kilometers every single day. Your phone works because engineers took time dilation seriously enough to build the fix into the system. The clocks on those planes didn't just display a different number. They aged less, and the atoms inside them completed fewer oscillations. Full stop. Whatever process was ticking away inside those clocks ran fewer cycles, and that's not a readout error or a calibration issue. Think about what that means for a person. Every biological process in your body is just a chain of atomic and biochemical reactions. So if the atomic clock slows down, the cells slow down with it. Your heart beats fewer times. Your cells divide fewer times. Your whole biological clock runs fewer cycles. The difference in elapsed time is permanent and physical. There's a clean way to think about why this happens. Your total speed through all 4 dimensions of space-time always equals c. Right now, sitting still in space, all of that speed points through time. So you move through time as fast as anything can. Start moving through space, and some of that gets redirected, so your rate through time drops. Speed up through space, slow down through time. Modern clocks are precise enough to measure this difference across just a few feet of elevation, like between the base and the summit of a mountain, and the numbers line up every time. Time isn't a backdrop, it's a rate, and it's yours specifically, tied to exactly where you are and how fast you're moving. What that means, practically, is that time is yours. It runs at a rate tied to your specific path through space-time, not some shared universal clock that everyone reads from. Space and time are inextricably intertwined in a four-dimensional structure, so when you move through space faster, you move through time slower. Someone moving faster than you isn't just measuring time differently. They're aging less. And when you meet back up, that difference is permanent and written into how many times their cells divided while you were apart. Motion is only half the story, though. Gravity does the same thing to time, and in some ways, it does it even more than speed does. That's where part 3 picks up.